Okay, so what I've done is I've got some polynomials here that we're just going to go through as many as we can. Okay, so the instruction is going to be the same, to find all of the zeros. So let's have a look at this one and see if we can, if our calculator will tell us what all the zeros are. Okay, so what I'm going to do is I'm going to put that in my calculator. I'm trying to get it to where there's not any glare. It's hard to do. Okay, put it there, it should do. So I've got x to the fourth minus 4x cubed minus 13x squared plus 40x plus 48. I'm going to start with a zoom 6. Okay, that's looking really good. I'm just going to refine this now. I'm going to press Window, and I'm going to take my x-min from -5 to 5, and I'm going to do my y from -1 to 1. All right, looks like I have an x-intercept at -3, -1, and at 4. Okay, so this polynomial has degree 4. So there are going to be 4 zeros exactly if we count the number of times a zero is repeated. So we can see that I have a 0 at -1 to -3, and it has odd multiplicity. It crosses through, and I would say it has multiplicity 1, because the higher the multiplicity gets, the more flattened you'll find it gets. Now, both of these have odd multiplicity, but looking at this, I would say that this one has multiplicity 1, whereas this one, we can see it's more flattened, so I would say that that has multiplicity 3. Something with multiplicity 5 would be even more flattened, but it's doubtful we'd ever see something with multiplicity 5. But the higher the multiplicity gets, the more flattening effect it has. Now, it's the same for even multiplicity. Remember, even multiplicity is it touches and bounces back. So I would expect something like that to have multiplicity 2. And then something like this it's more flattened, and so I would expect that to have multiplicity 4. Okay, so if it's odd multiplicity, it crosses through. If it's even multiplicity, it touches and bounces back. But also, the higher the multiplicity gets, the more flattening effect you see. So when I'm looking at this, I'm seeing, so here's my y-axis. I'm seeing a 0 at -3 and -1, and both of those look to me like they have multiplicity 1. And then I'm seeing a 0 here at 1, 2, 3, 4, because I have an x-intercept at 4. It touches and bounces back, and there's no flattening to that. And so that 0 at 4 looks like it has multiplicity 2. And you can see if I count up the number of zeros, the number of times they're repeated, they total up to the degree of my polynomial function. Okay, so that one was really easy to get from looking at the graph. Okay, now that's not always the case. Okay, so let's look at this one. So P of x is equal to this. And let's clear this out, and let's put that in our calculator. So x cubed minus 6x squared plus 12x minus 8. And I'm going to do a zoom 6 on that. Okay. Here is, I'm going to zoom in on this a bit. So I'm going to refine my X window to look something like that. And my Y window, I might take it from -2 to +2. So I'm going to press window. And I'm going to refine it for this particular one. Let's see what's going on. Okay, we can see that it is crossing through at 2, and we can also definitely tell that there is this flattening effect. So it has odd multiplicity because it crosses through, and I would venture to say, since it has that flattening effect, if it's multiplicity 1, it'd look more like that. I would venture to say it's multiplicity 3. So we have a 0 at 2, and it's repeated. It looks like it's repeated 3 times. And so if I write down the 0, the number of times it's repeated, then I will get exactly 3, which is the degree. Now, we could certainly check that with synthetic division. You could divide this by x minus 2 3 times. I'll leave that for you guys to do. But now, what if we've got something like this, and you're asked to find all of the zeros? Well, it has degree 3, so it's going to have exactly 3 zeros if we count any repeated ones, the number of times they're repeated. Let's see what happens when we put this one in. So I'm going to clear out the old one. So x cubed minus 8x squared plus 22x minus 20. And I'll do a zoom 6 on that one. Okay. Well, something seems to be going on there. Again, I'm going to refine my window. Okay, I do seem to be having a 0 at 2, but it does not have the flattening effect like the last one. It crosses through at 2, so it definitely has odd multiplicity, but it looks to only have multiplicity 1. Now, there have to be 3 zeros exactly, and from what I'm seeing here, this does not have multiplicity 3 because I don't have that flattening effect. How am I going to find the other zeros? And what's actually going on? Why are we only seeing one x-intercept? Well, only real zeros give you x-intercepts. If you have zeros that are not real, then you won't get any x-intercepts. And that's what's going on here. So the only thing we can do with this is to use synthetic division. So we've confirmed that 2 is a 0. You can do second graph, and you can certainly see here that 2 is an x-intercept, and so it's a real 0. And so I'm going to do synthetic division. And I'll start that going. Then we add. And then we add. So 22 minus 12 is positive 10, and then 10 times 2 is 20, and then we add. So I was expecting to get 0 there. So now I can rewrite p of x. And it's going to be the divisor, which is x minus the number in the box. 2 is a 0, x minus 2 is a factor, then times the quotient, plus the remainder, but the remainder is 0. These numbers give me the quotient. So remember also, P evaluated at the number in the box is equal to the remainder. So again, that's confirming that 2 is a 0. That's a definition of what a 0 is. So I can rewrite my polynomial P of x as x minus 2 times the quotient. So if I start here at the line, that's my constant, that's my coefficient for x, that's my coefficient for x squared. Now, if I want to get all of the zeros, I can certainly see that one of them is 2. I have another way that I can get the zeros for this. This is a quadratic. I could attempt to factor it because it is x squared by itself. But when I try and find two integers that multiply together to give me 10, and at the same time add up together to give me -6, I'm not going to have any luck. So the trick doesn't always work. But what will always work is the quadratic formula. So in your Canvas, I have put 2 videos of using the quadratic formula. One is if you have irrational zeros. It shows you how to get irrational zeros, and the other one is with complex zeros. So we remember, so you'll have to know the quadratic formula. So if I have this generalized form of a quadratic equation, and I want to solve that, in other words, find the zeros, then the solutions are going to be a fraction, negative b, plus or minus the square root of b squared minus 4ac, and this is really important, all over 2a. So often I'll look at students' work and I'll see that they only put the fraction part over the square root, and they had this out the front, and that's not correct. The whole thing goes over 2 times a. So for this one, we're going to have, my zeros are going to be negative b, so the negative of -6, because a is 1 for this problem, b is -6, and c is 10. So we'll have negative b plus or minus the square root of b squared. -6 all squared is positive 36, not negative 36. So you would have to put -6 in parentheses. So -6 all squared is positive 36, minus 4 times a times c, so minus 40. All over 2 times a, which is 2. So I can refine this. So that becomes positive 6 plus or minus the square root of -4 all over 2. Well, I can get the negative sign outside of this by rewriting this as the square root of 4 times I. And we do have to put our answers like that. And the square root of 4 is 2. And then at this stage, I would start splitting it up. So that gives me 6 over 2 plus or minus 2i over 2. And now I can do some cancellation. So I actually have 2 zeros here. It's 3 plus I and 3 minus I. Okay. So when I come back to find all the zeros, here, so the zeros, what are the zeros? Well, you set that equal to 0 and solve. We can see clearly 2 is a 0. But the zeros of this are 3 plus I and 3 minus I. So if we had to find all the zeros, that's where we have this. Okay. All right. So we have to remember somewhere in a previous math course where we've run across complex numbers, non-trivial complex numbers. Okay. Another mistake that I will see is students will say, oh yeah, okay, the 2 and 6 will cancel, give me the 3, and then the 2 and 4 cancel. You cannot do cancellation inside that square root symbol. Okay, so what I've seen before, I'll see something like this, and a student thinks that that cancels to 4. It does not. You can't do any cancellation inside here. 8 is not a perfect square, but it is the product of a perfect square. So I can write it like that. Whenever you have square root of 8, that's the better way to write it because you can do cancellation. Now I can make a cancellation there. Okay. So the square root of 8 divided by 2 is just the square root of 2. Okay. Now this raises the next thing that I want to talk about is if p of x is a polynomial function, with integer coefficients, and we can see here this polynomial function certainly had integer coefficients, then if a plus b times I, so that's a generalized complex number, if a plus b times I is a 0 or a root, they mean the same thing, and so is its conjugate. So again, sometime in the past we should have had know what the meaning of that is. So if you have a complex number and you want to take its conjugate, then you change the symbol for the number that's multiplied by I. So for example, that's a non-trivial complex number. If I want to take its complex conjugate, I change the symbol of the number multiplied by I. I don't change anything else. So let me show you how this same kind of question, instead of find all the zeros, another question using this could have been put to you. So let's let p of x equal x cubed minus 8x squared plus 22x minus 20. Suppose it is known that 3 minus I is a 0 or a root. What are the other zeros? Okay, well, this has degree 3, so there's going to be 3 zeros. We might have 3 distinct ones, or we might have one that's repeated, so we count it the number of times it's repeated. So we know that 3 minus I is a 0, so there's 2 more to find. This has integer coefficients, and so another 0 is the complex conjugate of that, which is 3 plus I. So that's my second 0. And then what are the other zeros? Well, I look at this in a graphing calculator, and I've got it in there. And you do a zoom 6, and then you'd refine your window, and you can see clearly that 2 is a 0. It has odd multiplicity. It's going straight through. It's not flattened, so it fits with the data here. So when we count these up, we get 3. Okay. So there's questions like this on the web work that's going to be due on Tuesday night. Okay. Let's go on with some more. We're down to this one now. So let's have a look at that. Again, let's see if we can find all of the zeros. Okay, this has degree 4, so there should be 4 zeros if we count any repeats, the number of times they're repeated. Okay, so I'm going to come here, I'm going to clear that. And remember, if you're graphing, make sure your plots are all clear. They should not be highlighted. Otherwise, when you do a zoom 6, you're going to get an error message. Okay, so I'm going to put this in my calculator. So plus 12x squared plus 80x minus 192. All right, just make sure I put it in correctly. Okay, then I'll do a zoom 6. Okay, so let me, it looks like I have one at -3, and it also looks like I have one at 1, 2, 3, 4. All right, it definitely has odd multiplicity and looks like 1, multiplicity 1. And this one, it looks to have that flattening effect. It's crossing through. So I would say that my zeros are going to be -4 is a 0 of multiplicity 1. And we also have it crossing through here. Oh, sorry, that's -3. My bad. And we also have a x-intercept at 4, and it's crossing through, but I definitely have that flattening effect to it. And so I'm going to say that that one's actually multiplicity 3. And if I add all of those up, and counting the number of times that it's repeated, I have 4 zeros. Okay. And if you press second graph, actually if I do second window, I don't want to look at the 0.5s. Okay. Okay. So I do have an x-intercept at -3, and I do have an x-intercept at 4. Okay, so it not only looks like it, but it is. Okay, and that 4 was flattened, and it's odd multiplicity, so it has to have multiplicity 3. So that works. Okay, so far with these two, we could see them and get the zeros from the graphing calculator. Well, what about this guy? Let me put him in. X to the 4th minus 8x cubed plus 13x squared, oops, plus 13x squared plus 24x minus 48. Okay, so let's see if we've got that one. Yeah, okay, so I'll do a zoom 6. Okay, here. So let's see what's going on with this one. There's one there, but I cannot see what it is. Same here. Okay, this one appears to be nice. Okay, so it definitely looks like I have 3 x-intercepts, and this one, 1, 2, 3, 4, has even multiplicity because it touches and bounces back, and I don't see any flattening. So this one looks like it has multiplicity 2, and it's a nice one in that it's an integer. It's 4. So if I press second graph, yes, 4 is definitely a 0. So it looks like 4 is a 0 of multiplicity 2. So I'm going to count it twice. But then I've got these other ones that are not real numbers, that are not integers. And if they are rational numbers, can be written as a simple decimal, it's not going to be a 0.5 kind of thing. So what I'm going to do to find that is I'm going to have to break this down with synthetic division. So I know for sure that 4 is a 0 and it's repeated twice. I know that for sure. So I'm going to get the ball rolling, and I'm expecting to get 0 here. If I don't, I've made a mistake. 1 times the number in the box, then we add. -4 times the number in the box, and then we add. -3 times the number in the box, and then we add. And 12 times the number in the box, and then we add. Okay, so now I can rewrite P of x as, so P evaluated at the number in the box is equal to 0. 4 is a 0. 4 is an x-intercept. We can see how it's all fitting together. I can also write P of x as the divisor, which is x minus the number in the box, times the quotient plus the remainder. Well, the remainder is 0. These are the coefficients for the quotient. So I start there. That's my constant, my coefficient for x, x squared, and x cubed. And now I know that 4 is a 0 and it's repeated. So what I'm going to do is I'm going to break this one down by using, because I've used up one of these, I'm going to divide this one using synthetic division with 4 in the box. So over here, I'm going to break this one down. I'm going to add. Okay, no, I've made a mistake somewhere. 1 times 4 is 4. And then I add, I get 0. Oh, 0 times 4 is 0, my bad. 0 times the number in the box is 0. And then we add. Get that. And because I knew I made a mistake because I wouldn't have gotten 0 there. -3 times that is -12. Then we add and get 0. Okay, so I can now rewrite P of x as, I'm copying this one. And now this one can be written as the divisor, x minus the number in the box, times the quotient. That's my constant, that's my x term, that's my x squared term. So my quotient here is going to be x squared minus 3, plus the remainder, which is 0. Okay, now it's been said before, if you have x squared minus a number, that always factors as x minus the square root of c times x plus the square root of c. So if I have x squared minus 3, I can factor that. And so that's what I'm going to do here. So P of x is x minus 4 times x minus 4. And then this will give me x minus the square root of 3 times x plus the square root of 3. When I have it factored like this, I can see what all the zeros are. 4, 4, square root of 3, and the negative of the square root of 3. If you were just going to find the zeros, you have 4 and 4, and then to find the zeros of that, you could have just put it equal to 0. So this is the kind of thing if you're asked for factorization. Okay, it helps when you factor it to see what the zeros are, but you could have also just thought, well, what will make that equal to 0? Add 3 to both sides, take square roots of both sides. When you take square roots of both sides, you get a plus or minus. That's where a lot of people go wrong. They forget the negative one. So this is why I prefer to factor it, because then you can see the two ones. But that will also give you the zeros, plus or minus square root of 3. And these are irrational numbers. And so you would not have been able to have written that as a decimal. And even if you tried to use the graphing calculator to tell you where those were, your graphing calculator is only going to give you an approximation. And that's not an exact answer. So if I put square root of 3 in, if I put square root of 3 in my calculator, well, that's an exact answer. But as soon as I press enter, that is not the square root of 3. That is a 9 decimal approximation to the square root of 3. WebWork will specifically tell you, do not put a decimal, put an exact answer. Now, how do you write that in WebWork? How would you have typed that in? You would have done 4, comma, 4, comma, then the square root of 3, comma, and then the negative of the square root of 3. So that's how you would write it in WebWork. Okay. I might have time to get a couple more in. All right, now something like that might look horrible. And you think, oh no. Well, maybe we can make it not so horrible with the graphing calculator. Let's see what happens with that one. It's degree 5, so there's going to be 5 zeros. So x to the 5th minus 5x to the 4th plus 23x cubed minus 33x squared minus 288x plus 702. Okay, I really need to check that, make sure I didn't make a mistake. Okay, now I'm going to do a zoom 6 and hope that I can see these. Okay, I've got one at -3, and okay. It looks like I have a 0 at -3. I should be able to see that. I do. And that I also have one at 3, and I do. And so I definitely have odd multiplicity at -3. It looks to be multiplicity 1. And then here at +3, it touches and bounces back, and there's no flattening there. So it looks like the zeros to this are going to be -3. It occurs once, has multiplicity 1, and then +3 occurs twice. Okay, so it has degree 5. There's going to be 2 more to find. Again, I can get there with synthetic division. I can use -3 to break this one down. So if you understand this degree 5 one, then anything else should be. So it looks like I'm going to have ones left over that are complex because I don't get any more x-intercepts on the graph. I had better get a remainder of 0, or I've made a mistake there. Okay, so I got -3, I add, and I get -8. get positive 24, and then we add, and we get that. Then 47 times 3 will give me 141. And then I add these two together, which is the same as 141 minus 33. Then I take that and multiply those together. And I might have made a mistake. Check it. Okay, so if I add those together, 324. No, I'm going to get, okay, so let me try that again. I have negative 5, then I have 23, then I have negative 33, negative 288, and positive 704. Try it again. That didn't look like it was going to give me 0. Okay. All right. So if I start there, that times the number in the box gives me that. And then I add, and I should get negative 8. Then if I multiply those two together, I will get a positive number, which is 24. Okay. And then I add these together, and I should be getting 47. And then I'm going to multiply that by negative 3 and get negative 141. Okay. And then I'm going to add those together, and I'm going to get negative 174. Okay. And then I'm going to multiply those two together, and I will get a positive number, which is 522. Okay. And then I add these together. So 522 minus 288 gives me that, and then times negative 3. Okay. So that is correct. So I can rewrite this as x minus the number in the box times the quotient. Plus a remainder, which is 0. Then I can break this one down because I've used up the negative 3, and I can do synthetic division twice with 3. And the goal is to get to a quadratic where you can use the quadratic formula. So we're probably, I don't know how much time we have left. So I can rewrite P of x as x minus negative 3, so that's an x plus 3. Then this one can be broken down as x minus the number in the box times the quotient. And I've used up one of the 3's, but I've got a second 3, and I'm going to use it on that one. Okay. Well, I'll go ahead and do this for that because I'm actually recording this on my thing. $26. So this will be x plus 3 times x minus 3. And then this breaks down to x minus 3 times x squared minus 2x plus 26. And then to get the zeros of that, use the quadratic formula. And I'm going to have negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That's negative 100. So the square root of negative 100 is 10i. So it's going to be 1 plus or minus 5i. So I come back here, and I'm going to have 1 plus 5i and 1 minus 5i. So those are my 5 zeros for that one. And there ends the recording.